Fillers in electrically conductive adhesives for electronic packaging, materials and filler technologies. Adhesives play an essential role in modern electronic assembly, where they are used both for structural bonding and for electrical conduction or insulation. Applications include the assembly of televisions, radios, and other electronic devices, where electrical pathways between circuit components must be reliably formed. Traditionally, lead-based solders have been widely used to create these electrical connections. However, environmental concerns associated with electronic waste and lead contamination have encouraged the development of alternative materials. Two important alternatives are lead-free solders and electrically conductive adhesives, ECAs. ECAs are considered promising next-generation interconnection materials in electronic packaging because they combine adhesive bonding with electrical conductivity. ECAs are composite materials composed of two main components: an insulating polymeric adhesive matrix, which provides mechanical strength and adhesion. Conductive fillers, which establish electrical pathways within the adhesive. Common polymer matrices used in ECAs include epoxy resins, silicone, phenolic resins, polyurethane, and polyimides. Conductive fillers may consist of metals such as aluminium, copper, nickel, gold, silver, tin, and zinc, or composite fillers such as SN bicoated copper particles. In these composites, the polymer matrix contributes mechanical stability and adhesion to substrates, while the conductive particles provide electrical conductivity by forming conductive networks. Electrical conduction occurs when conductive fillers come into contact or are separated by very small distances that allow electron tunneling. Based on the direction of electrical conduction, ECAs are generally classified into two types: isotropic conductive adhesives, ECAs, conduct electricity in all directions and are commonly used where traditional high-temperature soldering cannot be applied. Anisotropic conductive adhesives, ECAs, conduct electricity only in one direction, typically through the thickness of the adhesive layer. ECAs are widely used in liquid crystal display, LCD, assembly because they allow electrical connection between closely spaced conductor tracks without short circuits. The electrical and mechanical performance of ECAs depends strongly on the properties of the conductive fillers used. These fillers may be metallic, carbon-based, or polymeric. Metallic conductive fillers. Silver fillers. Among metallic fillers, silver, Ag, is the most widely used due to its excellent electrical conductivity and chemical stability. Silver can be used in ECAs in the form of powders or flakes and can be processed relatively easily. Other metals, such as copper, aluminium, and nickel, are less expensive alternatives, but they often exhibit electrical instability at high temperatures. These metals tend to form oxide layers on their surfaces, which reduces electrical conductivity by increasing resistance between particles. Silver has an advantage because the oxide layer formed on its surface remains electrically conductive. Silver-filled ECAs are widely used as alternatives to solder in electronic packaging technologies such as surface mount technology, SMT, chip-scale packages, CSP, ball grid arrays, BGA. Electrical resistance in adhesives containing silver flakes arises primarily from the tunneling effect between neighboring particles. When the separation distance between particles is extremely small, electrons can tunnel through the insulating barrier, allowing current to pass. Silver microfillers such as flakes, 3 to 10 micrometers, and microparticles, 2 to 3 micrometers, are often incorporated into polymer matrices such as epoxy or polyurethane. During curing, partial sintering of silver particles may occur, forming conductive microstructures that improve electrical conductivity. Polyurethane-based ECAs containing such fillers can achieve resistivities below 10 microohms cm after curing at approximately 150 degrees Celsius. Nanofiller enhancement. Electrical conductivity can be further enhanced by adding nanoscale conductive materials that act as bridges between silver particles. Examples include carbon nanotubes, CNTs, carbon black, hybrid systems containing silver nanoparticles, nanowires, and flakes. These nanomaterials fill gaps between larger particles, reducing tunneling resistance and creating additional conductive pathways. The concept of percolation is also important in ECAs. As filler concentration increases, a critical threshold is reached where conductive particles form a continuous network throughout the polymer matrix. At this percolation threshold, electrical conductivity increases dramatically. Silver nanoparticles and nanowires. The melting temperature of bulk silver is approximately 960 degrees Celsius, which is far above the temperature tolerance of printed circuit boards, PCBs. However, when particle size decreases to the nanoscale, the melting point is reduced due to the melting point depression effect. This enables nanoparticles to sinter at lower temperatures, allowing metallurgical bonding between particles. Adhesives containing 92 Wt% spherical silver nanoparticles, less than 10 nanometers, can achieve bulk resistivity values of approximately 8 times 10 to the power of 6 omega cm. However, very high nanoparticle loading can weaken the mechanical properties of the adhesive. To overcome this limitation, silver nanowires are often used. Their high aspect ratio allows them to create conductive networks at lower filler concentrations. ECAs containing 56 Wt% silver nanowires may exhibit bulk resistivity values around 1.2 times 10 to the power of 4 omega cm while maintaining improved mechanical strength. Adhesives containing nanowires also demonstrate higher shear strength compared with nanoparticle-filled systems. Silver-coated copper fillers. Copper nanoparticles are attractive because they are significantly cheaper than silver and possess low electrical resistivity and good electromigration resistance. However, copper easily oxidizes in the presence of oxygen and moisture, forming insulating oxides that degrade electrical performance. In addition, copper particles cannot be easily sintered at temperatures below about 300 degrees Celsius. To overcome these limitations, copper particles can be coated with nanoscale silver layers using chemical plating methods. These silver-coated copper particles combine the cost advantages of copper with the stability and conductivity of silver. Such modified fillers can be incorporated into epoxy or phenolic matrices used in ECAs. Adhesives containing silver-coated copper particles exhibit significantly lower electrical resistance compared with adhesives containing pure copper fillers. Long-term thermal exposure also highlights the advantage of these particles. In adhesives filled with pure copper, oxidation forms near the particle surface and increases electrical resistance. In contrast, silver-coated copper particles prevent oxygen diffusion and maintain stable conductivity. Electrical performance also depends on curing conditions. For ECAs containing approximately 23.5 volume% silver-coated copper particles, curing at higher temperatures produces lower electrical resistivity. Adhesives cured at 110 degrees Celsius may show resistivity values 5 times higher than those cured at 200 degrees Celsius. Low melting point alloy fillers. Electrical conductivity can also be improved by incorporating transient liquid phase sintering fillers. These fillers consist of two metallic components: a low melting point alloy powder, e.g., SNPB or SNIN, a high melting point metal powder, commonly copper. During curing, the low melting alloy melts and dissolves part of the high melting metal. The liquid phase then forms a new alloy that solidifies rapidly, creating metallurgical connections between particles. This process forms electrically conductive pathways while the polymer matrix provides adhesion. Another approach combines silver flakes with low melting alloy fillers. When the adhesive is heated, the alloy melts and forms metallurgical connections between silver particles and the metallized substrate, improving both electrical conductivity and joint reliability. Carbon-based conductive fillers. Carbon nanomaterials have gained attention as conductive fillers due to their excellent electrical, mechanical, and thermal properties. Carbon nanotubes. Carbon nanotubes, CNTs, may exist as single-walled CNT, SWCNT, double-walled CNT, DWCNT, multi-walled CNT, MWCNT. MWCNTs are commonly used in ECAs because they possess high electrical conductivity, high tensile strength, and large Young's modulus. When incorporated into adhesive matrices, they enhance both mechanical strength and electrical conductivity. Graphene. Graphene consists of a single atomic layer of sp² bonded carbon atoms arranged in a two-dimensional hexagonal lattice. It is extremely strong and exhibits exceptional electrical properties. Key properties include electrical conductivity around 6,000 Siemens per meter, Young's modulus is approximately 1 terapascal, tensile strength near 130 gigapascals. Graphene can significantly enhance both the electrical and mechanical properties of polymer composites. Moreover, large quantities of graphene can be produced at a lower cost compared with carbon nanotubes. Both CNTs and graphene possess large surface areas and high aspect ratios, enabling them to form conductive networks even at low filler concentrations. However, Proper dispersion within the polymer matrix is essential to achieve optimal performance. These carbon nanomaterials are also commonly used as auxiliary fillers together with metallic fillers such as silver flakes to enhance conductivity by forming additional conductive pathways. Reduced graphene oxide, RGO. Reduced graphene oxide, RGO, is a derivative of graphene that exhibits high electrical conductivity as well as good mechanical and thermal stability. RGO is often incorporated into epoxy-based ECAs as a nanofiller. When RGO content increases from 10 Wt% to 50 Wt%, both through thickness conductivity and in plane conductivity increase because interconnected RGO networks form within the polymer matrix. As a result, the insulating epoxy matrix becomes electrically conductive. Mechanical properties depend strongly on filler concentration. Moderate RGO content increases shear strength due to improved interfacial interaction between the filler and the epoxy matrix. However, excessive filler loading increases the viscosity of the adhesive, reducing its flow and causing micro-void formation, which lowers mechanical strength. Impact strength shows a similar trend. It initially increases with filler loading but decreases after exceeding an optimal concentration. In contrast, tensile strength of RGO-filled adhesives may be lower than that of the pure resin. Polymeric conductive fillers. Conductive polymers can also be used as fillers in ECAs because of their electrically conductive pi-conjugated structures. Examples include polyaniline and polypyrrole. Polypyrrole nanoparticles. Polypyrrole, PPY, nanoparticles can be added to silver flake-filled ECAs to enhance conductivity. However, PPY is a semiconducting material and has lower intrinsic conductivity than silver. Consequently, after a certain concentration, further addition of PPY nanoparticles reduces electrical conductivity. Polypyrrole nanotubes. Polypyrrole nanotubes, PPYNTs, provide better performance because of their high aspect ratio and good dispersion in organic solvents. These nanotubes can form continuous three-dimensional conductive networks when incorporated into ECAs. For example, in thermoplastic polyurethane-based adhesives filled with silver flakes, adding 0.5 Wt% PPY nanotubes can reduce electrical resistivity from 450 × 10 to the power of 5 cm to 346 × 10 to the power of 5 cm. Increasing the nanotube concentration to 3 Wt% further reduces resistivity to 5.8 × 10 to the power of 5 cm. However, beyond this concentration, aggregation of nanotubes occurs, which disrupts conductive pathways and increases resistivity. The improved conductivity results from the nanotubes acting as bridges connecting adjacent silver flakes, thereby reducing tunneling resistance. Such systems are particularly useful in flexible electronic devices. Dopamine-modified polypyrrole, surface-modified conductive polymers can further improve filler dispersion. Dopamine-modified polypyrrole, DAPPY, has been used as a co-filler in epoxy ECAs containing silver flakes. Unmodified PPY tends to aggregate, which separates silver flakes and reduces conductivity. In contrast, DAPPY disperses more uniformly due to the interaction of dopamine functional groups with the polymer matrix. This improved dispersion enables DAPPY to connect separated silver flakes, forming conductive bridges that enhance electrical conductivity. However, excessive DAPPY loading eventually reduces conductivity because it separates silver particles and increases contact resistance. Conclusion: electrically conductive adhesives are increasingly important materials in electronic packaging as environmentally friendly alternatives to traditional soldering technologies. These composite materials consist of a polymer matrix combined with conductive fillers that form electrical pathways. Metallic fillers such as silver remain the most widely used due to their high conductivity and stability. Advances in nanotechnology, including silver nanoparticles, nanowires, and silver-coated copper particles, have significantly improved electrical performance. Carbon-based nanomaterials such as carbon nanotubes, graphene, and reduced graphene oxide offer additional improvements in both mechanical and electrical properties. Conductive polymers such as polypyrrole further expand the range of filler options, particularly for flexible electronic applications. Despite significant progress, challenges remain in optimizing filler dispersion, balancing electrical conductivity with mechanical strength, and reducing material costs. Continued research in filler design and composite microstructure will play an important role in the development of high-performance electrically conductive adhesives for advanced electronic systems.